Hello everyone. Today in this video our new topic is Nernest heat theorem. So let's start with, we know that the Gibbs-Helmholtz equation is del G is equals to del H plus del G upon del T at constant pressure. So here when we move H toward this, it converts into negative sign, then it's convert this, and del G is a change in the free energy, del H is a change in enthalpy. When T is equals to 0, all term became 0, so del G is equals to del H. So Richard, so the experimental value of this is decreases at T decreases. Nernest relay this data and made an important suggestion to the value of this one approaches to 0 as the temperature approaches to the absolute 0. So absolute 0, del G and del G meet at a short region above the absolute 0. This coinciding with each other at the absolute 0 then show that the full line is not by dotted. So here you can see dotted line curve reveals that the true value of del G and del H not became equal to each other at absolute 0, but that approaches to each other became rapid, so not gradually. So here you can easily see postulate of Nernest and the expression is known as Nernest heat theorem. So this one is approaches as 0. We know law of thermodynamics. What is the consequences of Nernest heat theorem? As this one is minus del S change in entropy, so by the Kirchhoff equation this is equals to del Cp, difference in the heat capacities as the product and reactant. So here del S minus is equals to 0. Entropy changes to approaches 0, that the difference between two heat capacity of the product and the reactants also tends to approach 0 as the temperature is lower to the absolute 0. Nernest heat theorem hold good for in the case of solid. Since there is no gas exist at 0 Kelvin, Nernest heat theorem cannot apply to the gases. It also not apply to the cases of liquid. So here we came with the proof of the Nernest heat theorem. Consider a system which undergo a reversible adiabatic process from A to B. So SA is equals to SB. So value for this one is equation first and this is equation second. When we equate SA is equals to SB, so here equate this. So here you can see state A and state B, reversible adiabatic process, then temperature T1 to T2. So here state B attains 0 at TB is equals to 0. So this one is SB minus SA. Suppose during the eccentric process state B attain absolute 0, TB is equals to 0. So this one is SB minus SA dot. Equation 10 is not negative in an integral form. So this one is right. This is not correct as the impossible to attain 0. Both inequality are satisfied. So here you can see S is equals to SB. S dot is equals to S dot B. So what this is theorem proved. Applications. What is the application of Nernest heat theorem? Calculation of del G and del H. Application to the gaseous system. Transit point to the sulfur and EMF of the voltaic cell. So here come with the EMF of the voltaic cell from the Nernest heat theorems. EMF employed thermal data. This one, so the reaction and the heat change. So second application is transition point for the sulfur. The transformation of alpha beta sulfur, this one. So this is from the measurement of heat capacities, beta found 2.30 10 to the minus 15. So here you can easily see. Third one is calculation of del G and del H with the, as I have earlier proved, application of the gaseous system. So what is the limitations? Only good for solid. What is the limitation of Nernest heat theorem? Only good hold for solid. There exists no gas at absolute 0. Nernest heat theorem could not apply it for gas as well as liquid. If the substance exists in the two separate states, crystalline or supercooled, then the conversion of the crystalline to supercooled or vice versa, there is no entropy change. But experimentally, entropy of supercooled is greater than the entropy of crystalline at a low temperature. No good for substance. So this one is our topic. So thanks for watching. Bye bye. If you want notes of this topic, you can write on comment section. So bye bye.